In this video, we're going to talk about a very commonly used and very powerful way of sorting numbers using a technique called merge sort. Merge sort is one of those sorts that belong to the divide and conquer family. As you know, divide and conquer is a very old technique and implies is to take a problem and subdivide it into smaller problems with the idea that the smaller problem, because it has a smaller size, it will be easier to solve. Once we solve the little problems, we can put them together and find a solution for the original problem. So a merge sort is a divide and conquer sort in the sense that in order to sort values, which we're going to assume are contained in an array, we're going to divide the array in halves and keep repeating the process until we get to have subarrays exactly of length 1. So we start with one big array and we end up with a bunch of little arrays. That's the division part. Then we're going to take those little arrays, which have exactly size 1, one value in each of them, and we're going to merge them. And then we'll end up with arrays of length 2, then arrays of length 4, followed by arrays of length 8. They're going to be powers of 2. When I go through the example, you're going to see exactly what I mean. So as usual, we're going to start with a series of random values, and I'm going to use numerical values because they're easy, but this technique can be applied with integers or doubles or string objects or any object of your choice. The first step is going to be to partition the array in exactly 2 halves. And conveniently, I started with 8 numbers. So if I'm going to divide them into 2 halves, I end up with 2 arrays, each of exactly length 4. What would happen if the numbers are not even but odd? Then one array will have 4 elements and the other array will have 3 elements. Or one array will have 100 elements and the other array will have 99 elements. So it doesn't really matter that we're dividing them in exactly half. We're partitioning them into 2 groups. And one group could be larger than the other. So once I do this, then my second step is to take each of those halves and again partition each half into 2 subarrays. So now I'm going to end up with 4 subarrays. And here are my 4 subarrays. Notice that at this point, all I'm finding is the middle of the array and then copying values into the new arrays. None of the values are swapped. They are not exchanging positions. They are not being compared either. I just find the middle of the array and then simply divide that into halves if possible, and then just copy the values. In real life, if I have thousands of elements, I will keep doing this until I hit a point where all my subarrays are exactly of length 1. So if you look at my example, my next step here will be to divide each of these subarrays that have currently length 2 into subarrays of length 1. And that's exactly what I have. So what you see here is a collection of 8 very small arrays. 8 arrays, each of them of length 1, each of them with exactly 1 value. At this point, I have finished with the divide part or aspect of this algorithm. And now what I need to do is my last step, which is to merge these subarrays in order. And again, it's going to take several steps, several iterations, probably done recursively, but I'm going to be doing that until all the values are merged. But when I merge them, I'm going to merge them in order. Let's go through that. So my first step, okay, in my process, remember we are here, I have 8 small arrays, so I'm going to merge the first 2 into an array of length 2. And when I'm talk about these 2 values, I'm going to merge them in order. So the result is a subarray that has 2 values, 14 and 29, which happens to be in order. Next step, the next 2 values, and again merge them into an array that has length 2 and copy the values in order. So that gives me 13 and 37. And then I'm going to merge 40 and 25, and that's going to give me 25 and 40. And finally, the last 2 numbers are 32 and 64, and that gives me the last array of length 2 with those 2 values. Next step, merge these 2 subarrays into a subarray of length 4. And that's exactly what I have done here. And I have, again, inserted the values in order. And then I'm going to take the next 2 subarrays, which are these two, and I'm going to merge them into an array of length 4 where all the 4 values are going to be in increasing order. So notice, and again try to visualize this with arrays of 100 elements. So I'm going to have an array, let's say, of 100 elements where the 100 elements are in order. So here I only have 4 values, they are in order, 4 values, they are in order. And now the last step is going to be to merge these two halves. At one point I'm going to reach that level. I only have 2 arrays, perhaps very large arrays, and all I have to do is to merge those 2 arrays into a single one. And when I merge them, I'm going to do it in order. So I'm going to take these 2 subarrays and I'm going to merge it into one. And as I merge them, I'm going to merge them in order. So the end result is an array, one array that has all their values in increasing order, which is what I want to do. Notice a couple of things in this step. When I merge this subarray with this one on the right, notice that what I do is simply compare the value of the first element here with the first element in the second half and determine which of those 2 is the smaller. And obviously 13 is the smallest of them too, so I'm going to put 13 on the first position. And because these are arrays, my algorithm is keeping track of indexes. So now I know that I'm looking at this value and I'm still looking at 25. So I compare 14 and 25, and again 14 is smaller, so 14 is the one that goes into the array. And notice how they're being inserted in order. And again, I know that I'm looking at this value here and it's still looking at 25, and now 25 is the smallest of those 2. I insert 25. Now I'm looking at 37 and 32. The smallest is 32, insert 32 in there, and then next 2 are 37 and 40, and then the smallest one is 37. Very important. Once I finish inserting 37, my algorithm will recognize that I am out of elements in this half. One of the half that I want to merge, I have used up already. All the values have been inserted in the right position. So what happens now? There is no more comparisons. Very important. No more comparisons. So what the algorithm does is to say, oh, I still have these elements that need to be inserted, but they're already in order. I don't need to compare them. I don't need to sort them. All I'm going to do is to copy them. So I copy into my array the value 40, and I copy 64. So very important to understand that very last step. At the end of my algorithm, of course, all my values are sorted in increasing order. One of the things to notice, and I'll discuss that in a minute in the analysis, is that there were no swaps. In other words, when I start dividing, these 2 numbers belong to the first array. I'm not swapping their positions. I'm not comparing those values. When I try to divide these 2 subarrays, again, there are no comparisons. Simply, I'm splitting them into 2s, and one more time, I'm splitting them into halves until I have arrays or subarrays of length 1. Okay, so there is no comparisons at this point, and there are no swaps. Now, when I start merging them in order, of course, I have to compare. So I'm going to take these 2 subarrays, and I compare the first one of one subarray with the first element of the another subarray, decide which one is smaller, and put that on the first position. When I get to this point, I'm going to do the same thing. I'm going to take the first value of one subarray, compare it to the first value of the other subarray, decide which one is the smallest, and insert that into the first position. So merging the subarrays does require comparisons, but again, there are no swaps. That's what makes this technique very, very fast. So let's do some more formal analysis. Of course, if you were to take a look at the algorithm, it's going to be a recursive algorithm. What we're doing is repeating the same process, divide by 2, divide by 2, divide by 2, until we get subarrays that have exactly one element. And then merge 2 at a time, merge 2 at a time, merge 2 at a time, and eventually we get to merge 2 halves, and when you merge 2 halves, you have the whole array. As I just pointed out, there are no swaps at all. What we do is to split arrays by half and then merge them using comparisons. But very important, there are no swaps, there are comparisons. So the algorithm analysis is as follows. Let me assume that we have n numbers of elements, And for convenience, let me assume that these numbers of elements is going to be a multiple of 2. It's going to be 2 to the power of something, which I call k. So I'm going to have an even number of values. That's perfectly okay. If you say, well, what would happen when n is an odd number? The analysis applies, but for simplicity, we're going to assume that the numbers of elements is not only even, but that is a power of 2. So if we analyze 2 to the k, then k represents the level of recursion, meaning how many times we're going to apply the recursive call that says we need to split by 2. And every time that we apply a recursive call that says you need to split by 2, there has to be later on a corresponding recursive call that says you need to merge this. So if I split 4 times, then I'm going to have to merge 4 times. If the numbers of splits is 1,000, the numbers of merges is going to be 1,000. So going back to this formula here, if the numbers of elements is some value which is 2 to the power of k, what is the value of k and what does it represent? Well, k represents the numbers of partitions, how many times I'm going to divide by 2. And the value of k is simply log base 2 of n. We had seen this in other algorithms, for example, in binary search and in binary trees when we divide by 2 and we get the same type of performance or efficiency. Now, how many times do I have to divide by 2? Well, that depends on n. So I'm going to say that is O n. So now I need to say, okay, how many times do I need to divide by 2 and make a simple multiplication, and this is going to be then n log base 2 of n. So the efficiency, the expected, remember expected means average running time of the merge sort is n log base 2 of n. So this is actually faster than any sort which is n squared, and it works very, very nicely. Now there is a disadvantage or an inconvenience, a limitation of merge sort. Because we are dividing our original array into half, because we are splitting into many subarrays, then we're going to need memory to create the divisions, to create these smaller subarrays. And then we need to merge them. So the process of partitioning the original array into half and the process of merging those partitions into the original array requires extra memory. Other than that, there are no other negative or inconvenient aspect of the merge sort.